Okay, let us start. In the last class, we have derived the character table for the point group C2V, but we didn't quite finish it. So let us systematically go through the features of this character table again. So in general, a complete set of irreducible representations of a point group defines character table. So you see here the respective character table. Now let us analyze what the components of this character table is. So to the very left, we see that we have the point group symbol in the left upper corner. In this case, this is C2V. And in the same column below, we have the symmetry types for all the irreducible representations that exist in this particular point group. In the case of C2V, this is A1, A2, B1, and B2. Okay, so then you see here another block of multiple columns. So these are these are columns for non-conjugate symmetry operations. So in this case, we have the identity, we have the C2 symmetry operation, the sigma V XZ symmetry operation, and the sigma V prime symmetry operation. So these two sigma V symmetry operations are not equivalent, they are not conjugate, so they are in different columns. So you see here underneath the symmetry operations, there are the characters for the respective irreducible representations. So for A1, for instance, the characters are 1, 1, 1, 1. For A2, they are 1, 1, minus 1, minus 1, and so forth. And we've gone through this in detail in the last class. So then here to the right, we have the mathematical functions. So we have here in this column linear functions, as well as square functions, and the position of the respective functions within that column tell what symmetry type belongs to a particular function. So for instance, any linear function of Z is here in the row for the irreducible representation of the symmetry type A1. That means that any linear function of Z is of the symmetry type A1. So here to the right, we have the square functions. So you see, for instance, x times 3 in the row for the symmetry type A2. This means nothing else but that any mathematical functions that is a product of x times y has the symmetry type A2 in the point group C2V. So now you see actually here also some symbols you are not familiar with yet: Rx, Ry, and Rz. So these symbols stand for rotation around X, rotation around Y, and rotation around Z. So we are talking here about basically what and the position of these symbols are defined by what is, the symmetry operations do with the so-called rotational vectors. So we can only have linear vectors, but also rotational vectors that rotate around a particular coordinate. So for instance, we can, for instance, choose RZ, yeah, which you see here in the row for the symmetry type A2. So this means that rotation around Z has the symmetry type A2. We can verify again that this is the case by looking at, well, what the symmetry operations do with the rotational vector. So you see here a bend arrow which rotates around the Z-axis, representing a rotational vector, and you see that in this case we are rotating clockwise. So now will we still rotate clockwise after we carry out the symmetry operation C2? Well, as we rotate this vector here by 180 degrees, well, it moves to the left side here, but we see it still rotates clockwise. So that means the direction of the vector isn't changed, and therefore the associated character in the respective irreducible representation needs to be +1. So that means that rotation around RZ should be of an asymmetry type. Okay, so now let's look at the other two symmetry operations, sigma v and sigma v prime. So what does sigma v do? We have again here our original vector, but if we now reflect at a mirror plane which stands well within the board plane or within the paper plane, then you see that the resulting vector here changes its direction. Okay, it now actually rotates counterclockwise. So it has reversed the direction which is associated with the character of -1. So the same is true for the sigma v prime symmetry operation. So in this case, we are mirroring here at a plane that stands here in this position. That again changes the direction of the vector, and therefore the character is -1. So this way we have shown that indeed rotation around Z is associated with the symmetry type A2. We could show the same also for the Rx and the Ry values, rotational vectors using analogous arguments, but I'm not going through this here explicitly. Okay, now a few other properties of a character table. The order of a point group is equal to the number of symmetry operations. We can easily read the order of a point group from a character table. We only need to count the number of the operations that we see actually listed here. So in this case, the order of the point group would be 4. So the sum of the characters under E, whereby E stands here for the identity, defines the dimension of the point group. So in this case, the dimension is 4 because we have here 4 times the character 1. So each character table has a totally symmetric irreducible representation in which all characters are 1. You see that in this case, this irreducible representation has the symmetry type A1. The totally symmetric irreducible representation is always listed first in the character table. Okay, and you see that this is the case here for the point group of C to V as well. Okay, so now we are finished with the character table of the point group C to V. Now let's go to more complicated character tables. So thus far, everything was relatively easy because in the point group C to V, the coordinates are transformed in a relatively simple manner. Either the algebraic sign of the coordinate gets reversed or not. However, this is not true for all point groups. And in the following, I want to show you an example where we have a more complicated transformation of coordinates. Okay, so let us go from the point group C2V to the point group C3V, and let us develop the character table for the point group C3V in exactly the same in the same manner as we have developed it for the point group of C2b. So now, first of all, we should define a coordinate system. So we could define a coordinate system so that a molecule that belongs to the point group C3b, and we're choosing here the ammonia molecule, which is a pyramidal structure. We choose the coordinate system so that the x-axis is within the NH bond, okay, and the z-axis goes to the top of the pyramid and stands perpendicular to the trigonal base. Okay. Now, what is the principal axis in this molecule? Well, we have in this case as C3 axis as the principal axis, and the C3 axis stands exactly where the Z axis is, so we are rotating by 120 degrees around Z. So now, what would be the matrix representation of a C3 symmetry operation? So in order to approach this, let us look at the ammonia molecule from the bird perspective. And that means that we now have the x coordinate still pointing to the right, but now the y coordinate points to the top and the z coordinate points toward us. So now how will the coordinates transform as we carry out the rotation operation? Okay, so let us look at a particular point in this molecule within the x y plane. So this molecule is defined by coordinate x and the coordinate y, and we could define a vector that actually points toward the respective point with these coordinates. So now how will this vector change and how will the coordinates change as we carry out the symmetry operation? Before we actually go to a concrete C3 symmetry operation, let us make a more general consideration and let us see how the coordinates change as we rotate around an arbitrary angle theta. Okay, so let us just rotate around an arbitrary angle theta. And that will change the coordinate x into new coordinate x prime, and it will change the coordinate y into a new coordinate y prime. Okay, so now you see that in contrast to a C2 symmetry operation where we actually rotate around 180 degrees, in the more general case of a general rotation, and we do not simply flip the algebraic sign of one or two coordinates. We transform the coordinates in a more complicated manner. Okay, so the way the coordinate x is being transformed actually determines also how the coordinate y is being transformed. Therefore, we can say that these coordinates now transform dependent from each other. Okay, that makes these two coordinates, I would say in group theory, degenerate. Okay, so how do these coordinates transform? This is determined by trigonometry. And if you apply trigonometry, and I do not go through the exact mathematical steps here, then the new coordinate x prime is given by this formula here. It's x times cosinus theta, again theta is the angle on which we rotate, minus y times sinus theta. So y prime is equal to x times sinus theta plus y times cosinus theta. You see again here that x and y are dependent. The transformation of x into x prime also involves y, and the coordination the transformation of y to y prime also involves the coordinate x. So with this knowledge now, we can find the transformation matrix, which is associated with this particular rotation. Okay, so like in the point group C2E and its associated symmetry operation, again, the matrix representation of a general rotation operation must give the new coordinates when multiplied with the old coordinates. So now the old coordinates are just x, y, and z. And now the new coordinates are, well, x times cosinus theta minus y times sinus theta, x times sinus theta plus y times cosinus theta, as we previously determined, and 1. So the z coordinate will not change. Well, this is actually a mistake. So this has to be actually z and not 1. I have to correct that. So z actually just remains z. So this 1 is actually incorrect. Okay. Now again, what is the matrix representation for the rotation operation in this case? Okay. It is actually this matrix here, and we could again verify using the multiplication rules for matrices that this matrix, when multiplied with the old coordinates, actually correctly gives the new coordinates. Okay, now what you see here is that in contrast to the previous matrix representations that we saw, we do not only have non-zero numbers on the trace of the matrix, which is here, but we have also non-zero characters on the on other positions, in particular on this position here and in that position here, and that's because of the dependency of the x and the y coordinate. Okay, so now we have to apply this particular problem to the C3 symmetry operation. So for the C3 symmetry operation, we'd have to consider C31 and C32. We would rotate around 120 to 140 degrees by convention anti-clockwise around the angle theta. So theta would be equal to 120 and 240 degrees respectively. So what values will our terms adopt? So the sinus of 120 degrees is minus the square root of 3 over 2. The sinus of 240 degrees is the square root of 3 over 2. The cosinus of 120 degrees is minus a half. And the cosinus of 240 degrees is also minus a half. So this refers to clockwise rotation. Okay, so 240 degrees anti-clockwise, which refers to a C32 operation, is therefore the same as 120 degrees clockwise rotation. And we have to consider this now if we insert these values into the transformation matrix. As we do this, the C32 operation adopts the following form. It is minus a half minus the square root of 3 over 2, 0. It is the square root of 3 over 2 minus a half, 0, and 0, 0, 1. The C31 symmetry operation adopts the following form. This minus a half plus the square root of 3 over 2, 0, minus the square root of 3 over 2 minus a half, 0, and 0, 0, 1. So we have now found the matrix representation of this C31 and the C32 symmetry operation. So now, in addition to the proper rotations, we also have 3 vertical mirror planes in the ammonia molecule. So what are their matrix representations? Okay. For the first mirror plane, the way we defined the coordinate system, the matrix representation is very simple. It has the form 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So again, you find here only non-zero characters on the trace of the matrix. So why is this so? Because this sigma v here is defined to be in the xz plane. Okay, therefore it contains the x coordinate and the z coordinate. Okay, the x coordinate and the z coordinate don't change as we carry out the symmetry operation. So therefore the characters here are just 1. The y coordinate, which stands perpendicular to this plane, well, change its algebraic sign. Therefore the character is -1. So then, however, there are 2 other mirror planes, and these, of course, they do not stand orthogonal to the first form, but a 120-degree angle to them. Therefore, they are not coplanar to a plane made of 2 axes. Okay. Therefore, again, the coordinates, in particular the x and the y coordinates, are being transformed into a more complicated fashion. They are dependent from each other. So for that reason, we find again non-zero characters on positions that are not on the trace of the matrix. So the second sigma v is actually this form here, and the third sigma v has actually this form here. Okay. Now we have found all the matrix representations for the symmetry operations in C2V. Well, we have still forgotten the identity, I realize. Of course, the identity has again this very simple matrix representation, which has the form 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So now, with the help of the matrix representations, we can again understand the character table for the point group C3V. So because the matrices are now more complicated, there are some new characters in the respective character table that we need to understand. So let us go to the character table of the point group C3V systematically, and let us see how we can understand the characters in that character table. All right, so we see here the column for the identity. So we see here the column for the C3 symmetry operations. Note that we have now two symmetry operations in this column, the C31 and the C32, because these are conjugate. Okay, we can also now get a better understanding of what conjugate means from a more mathematical standpoint. Conjugate means that the two, the two symmetry operations, they have the same characters in the respective irreducible representation. So in this case, it's 1, 1, and -1. Therefore, we can say that they transform the coordinates in an equivalent, similar way, which was our previous definition. So, so here over there, we have our 3 sigma v operations. So again, in this case, we have 3 in the same class, yeah, in the same column, because our 3 sigma v symmetry operations are conjugate, and that means that they have the same characters in the respective irreducible representations. Okay. So now, what are our irreducible representations that we have? We have overall 3. And the first one has the symmetry type A1. This is our totally symmetric symmetry, our totally symmetric irreducible representation. So you see this to the fact that all characters here are +1. So any linear function of z belongs to the symmetry type, as well as any function, it's a function of x squared plus y squared and z squared. Okay, so now our second irreducible representation has the symmetry type A2. So this symmetry operation has these characters 1, 1, and -1. So rotation around z belongs to the symmetry type, but no no linear function like any coordinate or square function belongs to that symmetry type. So last but not least, we have the symmetry type E. So the symmetry type E we did not encounter before. So the letter E stands for double degeneracy. Note, we should not confuse this E with that E, which stands for identity. So a symmetry type E means that we have a symmetry type which is double degenerate. So what does that mean? That means that we have equivalency or degeneracy between two mathematical functions or pairs of mathematical functions. Okay. So because of that degeneracy, we also have here unusual characters. So here we have a 2, for instance. Here we have a -1, and here we have a 0. So you see here the mathematical functions x and y are in parentheses. That means now that the coordinates x and the coordinate y's are degenerate. So any linear function of x and any linear function of y would also be degenerate. So you see over here other pairs among the square functions. So any function of x squared minus y squared and xy will be degenerate, and any function of xz and yz will be degenerate. All right. So yeah, I just explained this. Okay, so now how do we explain these characters here? 2, -1, and 0. We can explain them now through our transformation matrices. So let's look at them. So we see here the transformation matrix for the identity. Yeah. You see here one of the two transformation matrices for the C3 symmetry operation. We could choose either one of the two. And you see here one of the transformation matrices for this sigma V symmetry operations. We could again choose any of the three we have just chosen here, the most simple one. Okay, so now how do these matrix representations explain these characters here? So now, because the coordinates x and y are dependent, the character for the irreducible representation of the type A is determined by the sum of the characters on the trace of the matrix for x and y. Okay. So for the character underneath the identity here, that would be this one and that one. Okay. So would add these two together, 1 + 1, and that would explain that too here. So now how to explain this -1 here? Well, for a C3 symmetry operation, the characters here on the trace of the matrix are -1/2 and -1/2. And 2 times -1/2, well, this is just 1. And then this 0 is the sum of, well, this one and that -1. So 1 - 1, well, that is just 0. Okay. All right. So these degeneracies can only appear when Cn or Sn rotational axes of higher order of 2 are present. That's certainly the case in the point group C3V. It's not the case in the point group C2V. All right. So now, in addition to double degeneracy, you can also have triple degeneracy. Okay. So we already discussed that E indicates double degeneracy. That means the two coordinates are dependent on each other, transform dependent on each other. However, it can also be that 3 coordinates transform dependent on each other, and that then would be realized by a capital symbol of T. Okay, so in this case, X, Y, and Z are dependent. So again, these E's and T's can have primes or subscripts, and prime and the double prime, for instance, indicates that you have a symmetric or an antisymmetric situation with respect to sigma h. So for instance, we could have an E prime on E prime prime. So if the algebraic sign doesn't change when we reflect the sigma h, we would have 1 prime, and if the algebraic sign changes, then that would mean that we'd have 2 primes. You do not need to memorize that, actually. Don't expect this, but you should have an understanding of it, where these primes are coming from. We can also have subscripts like G and U. So G comes from the German word gerade, meaning even, and U comes from the German word ungerade, meaning odd. And G means, well, you have a situation symmetric relative to inversion center. And U means that our situation is antisymmetric with regard to inversion. So again, symmetric means algebraic sign doesn't change. Antisymmetric means algebraic sign changes. Okay. Now, one well, great use of character tables is that it directly tells us when two coordinates are degenerate. Also, it tells us when two mathematical functions are degenerate. And because orbitals are mathematical functions, they can also tell us when two orbitals are symmetrically degenerate. That has great use because symmetric degeneracy also always means energetic degeneracy or equality. And that, as we'll see in a little bit, is of great help for the construction of the molecular orbital diagram. So this degeneracy is not often not easy to see by inspection. So therefore, the character tables provide a great help. Just a quick look into a character table can tell you when two orbitals are degenerate. So for instance, in the point group C3V, X and Y are degenerate. So that directly tells us that the 2px and the 2py orbital in the ammonia molecule are degenerate. So now let us see if we could also find that out by inspection. Okay. Let's draw again here our coordinate system, x to the right and z to the top and y to the front. Then according to that, the px orbital would here point to the right, and the py orbital here would point to the front. So naturally, there would be a 90-degree angle between these orbitals. So one of the orbitals would contain an NH bond, while the other one would not. So therefore, the symmetric degeneracy is actually not obvious. We have a 120-degree angle between the hydrogen atoms, but the orbital is then in the 90-degree angle. So why would the px and the py orbital are being degenerate and equivalent? So is there nonetheless a way? Of course, the character tables would immediately tell us, but is there a way to say this also by inspection? The answer is yes. So we can find this out by applying the following rule, which says that if the application of a symmetry operation interconverts two orbitals, they must be degenerate. So you have to look now for at least one symmetry operation that interconverts these two orbitals. Okay, also not an easy task, but the task can be accomplished. And it's easier to do this when we look at the molecule from the bird's perspective. And you see here the three vertical mirror planes in the molecule, which go to the three nitrogen-hydrogen bonds, respectively. So now we can do a little trick. we can actually rotate the coordinate system by 45 degrees. Okay. Then our x-axis points this way, and there would be a 45-degree angle between this NH bond and the x-axis. Okay. And then the y-axis would point into this direction. Naturally, it has to stand a 90-degree angle relative to the x direction. All right. So now where would our orbitals be? Well, the px orbital naturally will need to point along the x-axis, and the py orbital would naturally need to point along the y-axis. Okay, so now it is fairly easy to see which is actually the mirror plane, which is actually the symmetry element that interconverts the two orbitals. Can you actually see what symmetry element it is? Well, it's this mirror plane here. So see what this mirror plane actually does with the two orbitals. So it will mirror actually this lobe with a negative algebraic sign from the right to the left, so that it actually superimposes this one. And it will mirror this lobe here from the left to the right until it superimposes this one. Okay. So therefore, I have successfully interconverted this px orbital into the py orbital. Of course, we could also do the opposite. We could interconvert the py orbital also into the x orbital. We could mirror this lobe here over there to the right side. Then would actually overlap with superimpose with this one. And this y lobe here would be mirrored over there to the other side. And it will superimpose them as well. So this way we have shown that indeed there's a symmetry operation that interconverts the two orbitals, proving the degeneracy of the two. So we are now actually at the end of the chapter of symmetry.